to the last part on production optimization series, which is speaking a bit about dynamic optimization and also some final remarks. So dynamic optimization is basically based on a control loop, okay, and this can be done with a model, can be done with the physical system, or it can be done with a combination of both. So we have a control variable. This control variable acts on the system. Okay. What I'm going to put here doesn't act directly, but we have a layer before that is the actuation. Layer, we need the actuator, and then on this side we have the sensing and instrumentation, and this one outputs the observed variable. We don't need to put two. The observed variable is then read by the controller, and the controller receives some set point, and based on that, the difference between the observed variable and the controller, then it writes the control variable. It sends a signal to the control variable. Okay, so just as an example, if you have a gas liquid gravity separator, horizontal gas liquid gravity separator, we have at the outlet of the liquid we might have a control valve. Okay, there are different ways, control schemes. I have the gas outlet and I have the inlet. And we have some level. We have the gas. Okay, and then we have liquid level, okay, measurement, and then that goes to a controller. Okay, the controller receives a height set point, and then after that it sends a signal to the actuator of the valve, okay, to see how to operate. So we're going to have an example how that system looks like. So we have, first we're going to make three signals, three plots. So we have, that will be, this will be the Q inlet of liquid. Okay, that will be something that simply what is more liquid coming to the separator. This will be the H, and this will be the Q out. Okay, the Q liquid that coming out. Okay, we're going to say here Q inlet, and we have Q out. Okay, and we have the H, which the H is essentially this guy here. Okay, so when we see, let's assume that we have incoming entering the separator. There is some sort of a slug, okay, which increase from a value on a very big. Okay, so then the H, it will experience also, maybe here was at a normal level, this will be the H set. Okay, but then at another point in time it starts to increase. Okay, it starts to go up. Okay. The Q outlet was at was also at the value, right? And then it remained at that value, okay? But then after the controller, it saw that the height is going up, okay? So then it simply for the next step, okay, for the next time step, it simply increased the value or opened the valve, okay? So increase the value of the However, due to the amount of liquid that is coming in, maybe the H continues to increase. Okay. Then at that point also the controller reads that height and then decides to increase even more the H, the open even more the valve. Okay. And at that point, maybe because you have reached already a value that where the H was coming in, essentially it's starting to be comparable with what's coming out, okay, then the H maybe won't increase that much. Okay. And remember, our set point is essentially down here. Okay, so that's where we should be. Okay, then maybe this one still increases. No, notice the controller still notices this increase in height, so maybe it increases slightly more the H, the Q out. Okay, and then the H starts to maybe go down or remain stable. Okay, then if you are increasing it, I'm running out of space here, but if you're increasing it even more, okay, then this one starts to go down, okay, because now what is coming out is more than what's coming in, and then it will be go down, down, okay, maybe it will cross down here, and then it will go up, go down, go up, and so forth, okay, and maybe this guy already starts to reduce it a bit, reduce. And after it sees this measurement that is increasing again, then it will probably increase, then decrease, then increase, decrease. Okay. But essentially, depending on the measurements you have, the controller takes an action and opens the valve or closes it depending on the signal that it's receiving. Okay, and essentially it's all the time delayed the step that we are using. Okay, this is in our case our delta t. Okay, we are taking a measurement and then we take an action for the next step, increasing the rate, but here it's still increasing, and then when it starts to go down, for example here I notice that it increases slightly, so I simply increase it even more, and then here it's starting to go down. Okay. So a similar strategy we could use for optimization, okay, and I'm just going to use control for and one thing I have to comment here is that to calculate this H for the next step, okay, so let's see here, to calculate H at a given time, okay, we need either a model, okay, which can be, in this case has to be a transient model, or we need also simply the measurement on the physical system. Okay. Also, we can apply this technique with a system which is not transient. Okay, for example, for our gas lift case, okay, we could our gas lift model that we have is simply steady state, right? But we can also apply to a using a steady state model. in which, for example, okay, the Q oil was only a function of Q gas injection 1 and Q gas injection 2. Okay. So in that case, that doesn't have any time in that model, but we evaluate the function in each time. We evaluate the function in each time depending on the value of QG1 and QG2. Okay, simply in every time that we are time 1, time 2, okay, time 3, time 4. I take a measurement, let's say for example in time 2, okay, then I decide on my Q, the controller finds, but let's make it not like that, but let's use it on a new slide. Okay, so for example, at every time, okay, you have T1, T2, T3, T4. So at T2, for example, you check QO, okay, QO, go into the controller, and then the controller has a logic. We're going to go very soon to find out the QG injection 1 and the QG injection 2 of the next step. Then on T3, then evaluate again the Q oil, which is a function of these two guys, okay, and then Q oil, let's call this Q oil 2, this, well, let's call it star, and this call it double star, will be going into the controller, and then it will go calculate the Q gas injection 1 and Q gas injection 2. Okay, so essentially I have a time effect that I'm executing that in every certain time steps, okay, with certain frequency. But essentially what I'm doing is I'm evaluating in each time a steady state model. Okay, one approach to make the controller optimize is to drive the derivative of QO with respect to Q gas injection 1 to be equal to 0, and the derivative of QO with respect to Q gas injection 2 also to drive it to 0. Okay. So that will be one example. I know that this function is convex, so I know it will be increasing, so I simply instead of saying that, remember it works on a set point, some control loops. So this set point, what I'm saying is essentially will be 0. Okay, you want to drive that derivative, partial derivative, to 0. Okay, this is an example exactly similar to what I described. Okay, that is having again the same gas lift, two wells that are gas lifted. Okay, this is the gas lift injection of well 1 and well 2. And here you have the contours that are telling you the oil production. Okay, so you see here this is the maximum, and if you go in this direction, it's reducing the value for oil production. Okay. So you see you start on this is your starting point, and using this controller you are moving, so you read the gradient, okay, you read the QO here and QO here, and then based on that you shoot and you find the next Q1 and Q2. Okay, then you shoot next Q1, and here remember what we have discussed earlier, that in this line lies the point where the two derivatives are the same. Okay, and also remember the QO, Q gas injection 1 should be equal in the optimum to the QO, DQ gas injection 2. Okay. So it tends to be around that line. So this becomes like a set point that you want to be exactly on this region. Okay, and it's moving until it's maximizing it until it reaches to the maximum. And you have also the other case when it's constrained, because you have some amount of gas, it will increase the amount of gas until it reaches the bound. Okay, and there it just stops here. It cannot go further because the maximum, it doesn't have any more gas available. Okay. So just to end this session, it's some things about limitations and pitfalls of production optimization. One of them is your model. How good is your model? And usually we are based that your model is a good representation of the physical system. So if you have a poor model, it might not be that the solutions are the optimal points that you're computing. They are not representative, or they cannot be applicable to the actual real physical system. Okay. So one thing before embarking into an optimization production optimization project is to ask yourselves if is it actually possible to change the decision settings. Okay, sometimes we say, well, we want to change this choke, or we want to change the frequency of the pump, or we want to change the routing of a well. Okay, but might be that the equipment actuator is not available or is not functional. Okay, or is it could be that I'm not allowed to change that setting. I'm not allowed to change that setting. Okay, if you develop, for example, a optimization scheme based on control, and I need to control some variable, and I'm not allowed to do it because that variable is controlled by the system of a vendor, another vendor, for example, then I won't be able to do it. Or also the response time of the actuator, okay, especially for control of dynamic optimization schemes. Okay. Another thing which is also very challenging is that many, here you see is the NPV, or some um, revenue function as a function of the tubing diameter and the choke diameter. Okay, so you see in this case that it's very steep initially, the function for small choke diameters, but then it becomes very flat. Okay, so that tells you that when you start doing optimization, and during the first iterations, you're going to get a very huge increase in the objective function. Okay, but after that it becomes flat, and then it might take a long time to reach from this optimum to from these values to the actual optimum. So that is to say that like if you implement a production optimization project, it might be that initially you're getting very good increases, but then if to get this final increase, it might take a long time, and it might be quite challenging. Okay, because you have many functions that they have this, they're very flat, including the gas lift function. Also, there is a limit that you might wonder practical, what is the practical, the actual optimum, or the mathematical optimum, which is here, but isn't it good enough if we are close enough? Maybe the difference in revenue is 0.01%, and then it's not worth all the additional effort or the additional time that we have to put to get to that optimum. Okay. Other things is what I mentioned earlier is you can have local optima, local maxima. So when if you have, for example, a derivative based or a heuristic based, it might simply stagnate in one of these points, and you are missing essentially other optima that might be neighboring, that might be better. That's why the starting point is important. Always try with a different starting point. Running time, have to be sure that the running time that your optimization requires is suitable with the operational times. And short term versus long term, that's I'm going to there is a difference if you execute long term versus short term. Okay, so in some cases. So in this case, I'm presenting figures from a paper by Hassan Agus, and he's trying to maximize. These are the rates of each well per year. Okay, trying to maximize revenue NPV. Okay? And he did it in two ways. One is that you try to maximize the NPV of all years, considering all years. Okay, just summing, compounding the sum of all of them by changing the rate of all year. And there is the second approach is like a short term in which he's optimizing the revenue in every year. So he's changing the rates in each year such that you are maximizing only the revenue of that particular year. Okay, and here it shows the comparison on the two approaches. Okay, the red one is the long term when it's considering all the years. Okay, and it's considering the effect of all the years. And then the blue one is the short term. Okay, every year I try to make the best possible. Okay, and you see initially the blue one is better than the red one. I'm getting more and more revenue with time. Okay, but after some time it flips and I'm getting more and more revenue simply by using the long term. Okay, and this could be due to if you produce too much initially, you might be accelerating water coning, you might be accelerating gas coning, you might be accelerating something that causes a bad consequence later in the future, either by reducing the productivity of the wells, maybe by reaching a capacity constraint soon. Like here you have one example how the results were for the well. Okay, so that's the oil rate from well 3, the oil rate in time. And you see that you have the long term, which is the red one, and you have the short term, which is the blue. So the short term tells it essentially to produce the maximum until it reaches a point when reaching the constraint I have to close it. Okay, maybe it's a constraint in water production. But on the long term, actually I produce much less and I increase it gradually. Okay, and then I can simply continue producing that well for longer time. Okay, so final advice to include this lecture is before you embark on a production optimization project, just look at the rest of the list first. There are a lot of gains to be achieved. It's simply you look at the pressure drop pattern, failure pattern. You look at trying to improve and effectivize work processes. And the second point is that do you really need to do optimization? Maybe it's a trivial solution. So you don't need to set up a model, you don't need to set up an optimization algorithm, but simply you can do it with using common sense. Okay? After that, if these two you still go forward with it, you have to think carefully what is the main most important first order of magnitude problem, what really is affecting your KPI that you're concerned. If it's revenue, is it oil rate? Is it cost? Is it operational expenditures who are an issue? Is it the number of wells who is contributing most? Okay. Then you have to define, after you have clarified your problem, you have to define what is your objective, constraints and variables very clearly. Determine how relevant are the constraints. The constraints will modify. You see, they modify my problem. It can be a trivial problem, but if I add a constraint, it can be a non-trivial solution, okay? Because it restricts the domain of my function. But if I put too many constraints, maybe there are some of them that are completely irrelevant, and that makes and if I include them, that makes my optimization problem much heavier. Okay? Is it realistic to modify optimization variables? Again, the same related to the previous. If I am I relying on changing the choke opening, maybe the field has two old chokes that I cannot modify. Um, okay. Formulate your optimization in a smart way. Choose the right variable. We saw some examples where you have a nonlinear problem, very difficult to solve, but by doing some changes to the function, we can get a linear problem. Okay? And study how your input affects your results, especially on the system parameters. Okay? If now we say that the reservoir pressure will reduce with depletion, what will happen? What will happen with that optimum? Okay, end of the session. Bye bye.